about gases part one. Okay, this gas is broken down into part one and part two. Okay, uh, properties of gases. Gases have seven properties. Okay, the first property is they're fluid. Fluid does not mean liquid. Fluid just means that it has the ability to flow. Okay, glass is a fluid. Glass flows. Okay, if you look at some really old windows, you actually some super old windows, you can actually look at the top of them and you can see holes start to form in the top of a window because it moves very slowly, but it does move. The gravity does allow it to pull down. I know at St. Henry's, they when I was there before they redid some windows, they actually had some holes in some windows because it was thin glass to begin with, and they do flow down. So fluid is the ability to flow. Gases, this common sense. Gases have a density much less than liquids and solids. Okay, we know that gases have a density much less than liquids and solids. We know this because if you put a soda in, pardon me, an empty bottle, an empty soda bottle in a liquid, it's going to float to the top. Correct? It's going to float to the top. Same thing we know that in a soda bottle before you open it or drink, the gas is at the top. So the gas is at the top, not the bottom. Gases can be compressed. Their density can be increased by supplying pressure. Now, gases can be compressed to an extent. Pure oxygen is very hard to compress. Okay, people that are on oxygen machines have an oxygen mixture. It's not just pure oxygen, but you can compress a gas. You can compress a gas. Number four, gases exert a pressure on the surroundings. How can you tell me? How do you know a gas exerts pressure on its surroundings? Tire pressure. You put gas in, you put air is a gas. You put it in a tire, the tire goes up. A balloon. A balloon gets bigger because the gas is applying a force to the outside of it. Gases will diffuse into one another. Remember, diffusion from last year is in movement from areas of high to low concentration. Gases will mix. They will not separate if left alone. We know this because is our atmosphere separated? We're 78% nitrogen, 21% oxygen, so on, so on, so on. But is it separated? No, our body separates the nitrogen. We only breathe in the oxygen. But in fact, they don't separate into pockets. Gases can effuse. That means they can move through a tiny hole. We know this because has your tire ever gone flat without a big hole in it? Yes. And then the amount and properties of gas can be described using temperature, pressure, volume, and moles. That's what we're going to get to tomorrow and next week. Okay. Kinetic molecular theory, you can see this broken down into some shorter ways. Kinetic molecular theory says the gases are discrete molecules, which are very small and very far apart compared to their size. Here's the key thing in the kinetic molecular theory. They move in random straight line motion. A gas does not curve. Okay, a gas goes in straight motion. And this is the definition. The average kinetic energy of a gas particle depends on the temperature of the gas. We know the average temperature is the average kinetic energy. The collision between the gas molecules and the wall of the container are elastic. Elastic collisions, the energy before and after are equal. So a gas doesn't lose energy when it collides. Okay, it doesn't lose energy. Why does the balloon go flat? If gases don't lose energy when they collide, why does the balloon go flat? They don't lose energy, so why does the balloon go flat? Yeah, because they effuse out. They effuse out, they leak out. Okay, they leak out. The gas doesn't lose the energy. And the molecules exert no attractive repulsive forces, and they travel with constant velocity. Now, not all gases follow the kinetic molecular theory. Okay, an ideal gas follows the kinetic molecular theory. That's the definition of an ideal gas. We'll talk a lot about ideal gases next unit. That's actually the main focus of next unit is the ideal gas law. They do 100% follow it, but most gases are not 100% ideal. Instead, the what's called a real gas. Okay, that do not obey 100% the kinetic molecular theory because gases do have some attractive forces to them. Okay, gases do have some attractive forces to them. That's because of their polarity. Okay, their atomic structure, their electronic structure can cause those. We know carbon monoxide is very dangerous. It has that lone pair of electrons. It's polar, so it will be attached to other things that are polar. Did we talk about hydrogen bonding this year? Okay. Water vapor. I couldn't remember if we've done that or not this year. Water vapor. Water has hydrogen bonding, so each of those gas molecules can be attached to other gas molecules. Carbon dioxide can be attracted to it. That's how you get a cloud. Okay, how do you get a cloud? You get water with clouds. Most gases behave ideally. Now, not 100% ideally, but with this is why significant figures are important because they fall within they are significant. They behave ideally because they fall outside of the significant range. Okay. The biggest deviations occur at high pressure and low temperature. That's not a normal thing, is it? High pressure and low temperature. We know that the Earth's core has very high pressure, don't we? But we know the Earth's core is what? Hot. Okay. So that's the other way. On the other hand, low temperatures are typically found in mountaintops. Okay. Is the pressure high or low in the mountains? Pressure is low in the mountains. The pressure is low in the mountains. That's why, like sporting wise, that's why like the Colorado Rockies, the baseball parks, play typically home runs. There's not as much pressure there. That's why in Denver, Colorado, the kicker, it's easier to punt the ball there, kick the ball there. That's why anybody ever paid any attention to? I think scalloped potatoes are one of them. It gives you the instructions on the box to how to cook it. But it says at high altitudes, cook it at 400 degrees instead of 350 degrees. Anybody paying attention to that? Well, there are some foods that do that because they have different. There is less. That's one of the questions in your homework tonight. The pressure is less. The pressure is less at high elevation. Okay, there's less because there's less air pushing down on it. This at high pressure, low temperature is where gases start to become liquid. Pressure divided as force per area. Gases exert the pressure. The pressure is caused by the elastic collision. A barometer is a device that's used to measure atmospheric pressure. Where have you heard the term barometer at or barometric? On the news, we're talking about the weather. They're going to give you the barometric pressure. Okay, they're going to give you the barometric pressure. That's the pressure of the day. The barometric pressure can tell you a lot of things. You have high pressure, it's not going to rain. Okay, when a low pressure front moves in, that's when you're going to get rain. A hurricane is an extremely low pressure system. Okay, a low pressure system. Now, what happens when you have a high pressure and a low pressure system come into contact with each other? What tornadoes or large propensity, or at the very least, a lot of wind. Okay, a lot of wind. So that's simply why tomorrow it's going to rain Thursday. Tomorrow it's going to be very windy because our pressure is really high right now. Our pressure is above 30 inches of mercury. We know that that's not conducive for rain. But we know that it's going to rain Thursday, so that means the low pressure has got to come in. So tomorrow is going to be very windy because the high pressure and the low pressure are going to meet. Okay, and that's simply why. What time of the year is the windiest typically? Spring, and we know spring is a rainy season, don't we? Because our low pressure and our high pressure meet. Units of pressure are atmospheres. Pascals, the SI unit of pressure. Pascals are rarely ever used. Atmospheres will we will use the most. Okay, that's why that's one there. Kilopascals are used a lot more than pascals. This means 1,000 pascals to kilopascal. Millimeters mercury. The millimeters mercury was kind of the first measurement. Okay, and most barometers used to be mercury. Okay, and so what they would do is they would measure how many millimeters of mercury. What? How tall it was. Okay, that's where the millimeters of mercury come from. A torr is the same thing as a millimeter of mercury. A torr is the exact same thing as millimeter of mercury. And PSI, pounds per square inch, where do we use that? Where? Tire. Your tire tells you to fill it to 35 PSI or 40 PSI. Okay. Bars, I will say this, until last year, I had never, ever used a bar in my life as a unit of pressure. Okay. But I bought a new hay baler last year, and the pressure is actually in bars. Okay, I've never ever used it, but it is a unit in a millibars. Kind of the same thing there. So there were 8, so they had to put 7 on your quiz. Conversion factors. 1 atmosphere is equal to 101.325 pascals, 101.325 kPa, 760 mercury. I want you to put a decimal point there to indicate that that's significant. Okay. Put a decimal point on that to indicate that's significant. Same thing with the torr, okay? Put a decimal point after that to indicate that that is significant. So they indicate that that is being significant. And then 14.7 psi. A millimeter mercury and torr are the same thing. The millimeter mercury and a torr are the same thing. So today your homework is over conversion. Today your homework is over conversion. So we're going to, oh, let me put all my stuff right. New share. I need a calculator out. You don't need your Chrome. I mean, you don't need your. You need a calculator. You don't need your periodic table for this. You don't need your periodic table for this. Your periodic table, not this unit, no. Except on your naming quizzes. Okay, so our first example is going to say convert. Let's go with 2.00 atmospheres to, let's go to mmHg. Convert 2.00 atmospheres to mmHg. Now, when we're converting, we're going to use the same steps that we've always used. Okay, this is why I convert the same way when I taught you your metric, your SI and your metric conversions, your non-metric, because it always works. Okay, it always works. Miss Collier's way she taught it with moving the decimal, great way. It only works for the metric system. Not on this. Not on this. So, our first step of any conversion factor is to do what? Take what I know, put over 1. So, what do I know? 2.00 ATM and put it over 1. What's my next step? I'm going to multiply. What's my next step, though? What's going on the bottom of my fraction? I'm going to multiply by fraction. That's my next step. ATM. ATM. The unit on the top goes on the bottom. Okay? ATM. Now, what unit's going to go on the top? mmHg. There's going to be some 1 and 2. 1 and 2. Okay. Now, I just had that conversion list, didn't I? 1 always goes in front of ATM. 1 always goes in front of ATM. So what's the conversion factor between ATM and mmHg? 760. 1 always goes in front of ATM on this. So on this one, I just multiply, don't I? What's the answer? 1520? Decimal point or no decimal point? No decimal, because I need 3 significant figures. So 350 mmHg. Next problem. Convert 48.25 kPa to PSI. Convert 48.42 kPa to PSI. So what do you do first? Put 48.2 PS 48.42 kPa all over 1. I'm gonna multiply. What's gonna be in the bottom of this fraction? Not Aiden. kPa. What's gonna be in the top of the fraction? No. I heard the answer. ATM. If you're not going to ATM or starting ATM, you got to go through ATM. What's going to go in front of ATM? So 1 ATM. And what's going to be in the bottom? Nope. 1.1.325 kPa. So if you're not going to ATM or start with ATM, it's 2 steps, okay? If you're not going, it's 2 steps. So now my kPa cancel. kPa cancel. And what's going to be in the bottom? I got to do 1 more step because I want to be at PSI. What's going to be in the bottom of this next fraction? How many ATM? 1. 1 always goes in front of ATM. And on the top, it's going to be what? 14.7 PSI. Got the 14.7 from the conversion factors. So now this is 48.42 times 14.7 divided by 101.325. And I think you get, what's my answer? What? 7.025. So I started with 4, I want to end with 4, okay? These are exact numbers. These are exact numbers. So, did you answer your question? Okay. 7.025 PSI. That's like, is that a very high pressure? No. Yeah, I mean, in general, and this isn't 100% true, one ATM is equal to atmospheric pressure. That's where, on a normal day, your pressure is typically 1 atmosphere, okay? So it would be a 14.7 PSI. So your temperature, anything below 14.7 would be lower than what their daily PSI is. And I'm sorry, I got 7.025 PSI. I mean, 4 was not very high. I mean, 7 PSI wouldn't even register on something. Notice, if anybody pays attention, your tire gauge simply doesn't go below 15 PSI. Most tire gauges start at 20, 10 or 20. Most tire gauges don't even do that because unless something's pushed down on it, nothing's going to happen with that. Let's do another example. Yep. I haven't made up my mind. The lowest pressure ever recorded was 25.69 inches mercury. What is that pressure in ATM? 25.69 inches mercury. Now, this wasn't a thing on your conversion factors, was it? No. But we should have enough information to be able to solve for this. Okay. We're still going to do the same thing, aren't we? We're still going to convert, take what we know and put it over 1. So I know I have 25.69 inches mercury over 1. And what's going to be in the bottom of my next fraction? Inches mercury. What's going to be in the top of my next fraction? What? Millimeters mercury. Okay? Millimeters mercury. So, yes. So, I need to know a conversion factor. Do I know a conversion factor between inches and millimeters? You should know it. There's a conversion factor between inches and centimeters. And the easiest way to remember it is that in 1 inch mercury, there are 254 millimeters mercury. I was always taught, I don't remember decimals, I was always taught that in 1 inch, there's 2.54 centimeters. So I know millimeters, I just move it over 1 more. You're going to have a question like this, a couple questions like this on your homework today, okay? That's your conversion factor between them. 254 millimeters mercury is 2.54 centimeters mercury, okay? No, 254, no, not 254. An inch mercury. But there are 254 millimeters in an inch. That's wrong. That's wrong. That's wrong. 25.4. 100% wrong. 25.4. 100% wrong. 25.4. Bad teaching moment there. That should have been 25.4. Okay, 25.4. Now, I heard the answer back there somewhere else. What's my next fraction going to be? What? Yeah, MMHG on the bottom, ATM on the top. So I'm going to have 1 ATM on the top because 1 always goes for an ATM. And what's my conversion factor between ATM and millimeters mercury? 760 mmHg. If you look up the weather, if you go to weather.com, let's get this answer out first. What's the answer? Equals 0.8569 ATM. So that's a lot lower than 1, isn't it? That's pretty low. If you go to weather.com, you go to weather.com and you look at the weather, it gives you the pressure in inches mercury, okay? It gives you the pressure in inches mercury. So it means it's 29.78 in Denver, Colorado. That's one of your questions on your homework today. I can go to Charleston, Missouri, and you can see the pressure is, well, it's actually lower than it was a while ago. It's 30.36. Anything above 30, it's not raining, people, okay? Our pressure right now is 30.36 inches mercury. Yes, ma'am. How did I get that answer? I mean, I did 25.69. Yeah, that's correct. That's correct. 0.8586 is correct. 0.858. 0.8586. That's wrong. Gosh, Marshall. I'd say you trans. Yeah. So the answer equals, let me fix that, 0.8586. 85. All right, last thing we're going to do today is a little review over temperature. Convert 22 degrees Celsius to Kelvin. What's my equation? Now, this is not to put something you know over 1, is it? Other way around. So we know that Kelvin equals degrees Celsius plus 273.15. So I plug my stuff in. So Kelvin, and that's not degrees Kelvin, would equal 22 plus 273.15. And that equals what? That's wrong. Just something slightly wrong about it. 22 plus 273.15. Yeah. Significant figures, what's wrong? This has, when I add and subtracting, I care about decimals, don't I? Well, I care about decimals. So 22 has no decimals. 273.15 has 2 decimals. So my answer needs to have no decimals. So 295. So if you're going from Celsius to Kelvin, you add. Now, if you're going from Kelvin to Celsius, what do? Subtract. One more. 295. Am I not still presenting that screen? Oh, it's been a rough day with the Wi-Fi. I hope it's better for tomorrow. Hey, convert 72 degrees Fahrenheit to Kelvin. I got to go from Fahrenheit to Celsius, okay? So you look up, you got to go from Fahrenheit to Celsius, you look up the equation. And I'm going to copy and paste the equation. No, I'm not. We know that I got to go from Fahrenheit to Celsius first. So we know that degrees Celsius equal, and this is, this equation you're never responsible for memorizing. Degrees Celsius equals, will not be required for memorizing it. No. Fahrenheit minus 32 times 5/9. Okay. 5/9. Degrees Celsius equals Fahrenheit minus 32, close parentheses, times 5/9. I'll tell you what, let me do something. I'm going to fix it. What did I say? Convert 72 degrees Celsius? 72? Fahrenheit. And so our equation was degrees Celsius equals Fahrenheit minus 32 times 5/9. Why did you can't turn a microwave on with us, did it? Okay, so I'm going to plug my stuff in. So that's going to equal 72 minus 32 times 5/9. And now, significant figures, I need to start with pretty much how many I started with. So, and you got what? 22.1, 22, yes. You got like 22.22222, correct? So that equals 22 degrees Celsius. Now what do I need to do? Add 273. So Kelvin equals degrees Celsius plus 273.15. So this equals 295. So, any questions?